Hey everyone, Mr. Newman here. We're going to do a real quick video on slant asymptotes. That's another part of rational functions. We already learned how to graph them, but there's one more thing we have to worry about, and that has to do with the end behavior. So just remember that end behavior means as x goes to infinity or as x goes to negative infinity, the far, far right and the far, far left of the graphs. And as we're making these, some of these, if you remember, we had these rules, like if the power is bigger on top. By power, I'm talking about the degree, the leading coefficient. If the degree of the top polynomial is bigger than the bottom polynomial, there's no horizontal asymptote. And if they're the same, then the horizontal asymptote is this ratio of the leading coefficient divided by the leading coefficient. And if the denominator has a bigger degree, then the horizontal asymptote is 0 because remember, the numbers on the bottom get really, really big, really, really fast, way faster than the numbers on top get big. And so anything divided by a really, really big number is close to 0. So there is a caveat here. I need to put a star for that top one because just because the number, well, there is no horizontal asymptote, but sometimes we have to worry about a different kind of asymptote. And to look at that, I want to zoom in on f of x right here. This doesn't always happen. In fact, this only happens when the degree of the numerator is 1 higher than the degree of the denominator. What is it that happens? Well, notice right here, I've got x cubed on top and x squared on the bottom. So the degree is just 1 higher on the numerator. If I graph this, you might think, hey, this looks kind of like a polynomial just because at the end, behaviors can get really big really fast, right? Something like that, right? Well, the thing is, it's not getting that much bigger, that much faster than the number on the bottom. In fact, if we, it's not going to look like a parabola or any kind of shape that curves upwards at the end. It's going to look a little different. Let's zoom in right here on those first two, just the leading coefficients, the leading terms, okay? And I want to, let's say that those are the only things that matter. In fact, with the one exception, those, and right here in this function for sure, those are the only things that matter because as those get really, really big, those numbers on the right, the +1 and the -1, are basically irrelevant. They're so small. So I want to just write that down, x cubed over 3x squared. I can simplify that to x over 3, right? And of course, we've got to worry about domain restrictions. We can't plug in a 0, but if we're only talking about the number getting really, really positive or really, really negative, we don't care about 0 there anyway. So right here, we get x over 3, also known as 1/3 x. And what that means is that instead of the function getting really, really big, really, really fast like this, it actually looks a lot more like this, where this is a graph of 1/3 x. And see, it's getting big as you go to the right. In fact, it keeps on getting big forever, but it doesn't curve upwards. It actually increases at a steady pace. And so the function's going to approximate that. So what I want you to do right now, I want you to pause the video, okay, and type f of x into Desmos. So f of x, this one right here, I circled it in blue. And then I also want you to type in the equation y equals 1/3 x, that one we got right there, okay? Go ahead and do that right now, and I want you to jot down what you notice. All right, you paused the video. Answer the question here, and if you haven't yet, go ahead and pause it and make sure you answer that, because I want you to bring that to class and share what you notice. I'm going to talk a little bit about what you noticed. Hopefully you noticed that that your function f of x is getting closer and closer to that line 1/3 x. And that right there is called a slant or an oblique asymptote, all right? So this next kind of problem, we're just going to find that slant or oblique asymptote. And the way we're going to do that is we're actually going to use long division. So I have x plus 1 in the denominator, so I'm going to divide by x plus 1. All right, well that was nice. Let's see here. When I do this, I get, oh, it is not as pretty as we've been doing in the past, but that's actually a good thing because, well, there's a slant asymptote. So we have a remainder of 2. If you remember what that means we add 2 divided by what we're dividing by, x plus 1. And so that is the remainder that gets tagged on to the end. That's so important. I want to write that down over here, okay? I need to think about what in the world happens to this function as x approaches infinity. Specifically, that fraction on the right there. Well, if you plug in really, really big numbers there, then the denominator gets really big. And anytime you have a really, really big denominator and a numerator that stays the same or just doesn't get as big, you're going to be getting closer and closer to 0. And so this thing right here, that fraction, as x gets really, really big, really positive, and in fact it also happens with really, really negative numbers, that fraction gets closer and closer to 0. So we could just eliminate it when x is really, really large. And what does this mean? This is the slant asymptote we're talking about. Right here, x minus 2, the equation y equals x minus 2, that is the slant asymptote. And you can see another reason, or another approach of this, the reason this happens is when you divide this. Now what did I do when I divided this? All I did was this right here, I'll say this right here is another way of writing this function, because this function is dividing by x plus 1. They're just in different forms, okay? To find the slant or oblique asymptote, you just need to divide by the denominator, and you can figure out what the slant or oblique asymptote is. Now, there's only a slant asymptote when, remember, the exponent, the leading term, the degree of the numerator has to be exactly 1 more than the degree of the denominator. Otherwise, it'll be a horizontal asymptote or no asymptote at all. One interesting thing is, though, if you divide this, you'll get some kind of function right here, right? And whatever that function is without the remainder, as x gets really, really large, it's basically that function is what you're approximating, because this remainder term will always go to 0 as x gets really big. All right, let's use this now in a full graph. So I've got this function f of x, and I want to graph it. Okay. Well, first we're going to go through all of our steps, but you notice one thing we added were slant asymptotes. So first thing I want to do is factor it. That's going to help me out with a lot of this stuff. Let's find the y-intercepts. I'm going to plug in f of 0. If you notice, a lot of those x's become zeros, so we get -2 divided by -1, also known as 2. I'm going to be plotting them on the right there as we go, so just so we have them all. X-intercepts, that's going to be solving these two equations, because those are the zeros for the numerator, and we get x is 2 and x is -1, so I'm going to plot those 2 points. The vertical asymptote, that's when the denominator is 0. So let's solve this equation here, and you get x equals 1. So I have a vertical asymptote at x equals 1 right there. And lastly, our slant asymptote. So to do this, remember we have to divide. First of all, I do know there's a slant asymptote because the numerator has a degree of 2 and the denominator has a degree of 1. So I need to divide to find it. We divide, we get this. Oh, that's nice. That goes to 0, so I know that my remainder is 2. And that means I'm just going to add 2 over x minus 1. Well, remember, if this is my function as x gets really big, that is equal to 0, so I don't need to worry about it. So my slant asymptote is y equals, well, it's kind of weird. The only thing that's left is x, so y equals x. So let's graph that line. There's the dotted line right there. And lastly, let's fill in our additional points. This is the tricky part. Remember, I really only care about the vertical asymptotes and the zeros. I realized I went ahead and also put the y-intercept on there, so 0, 2, though that is not necessary. It's just helpful for me identifying that I'm filling out the points. Let's see, we also, okay, sorry, let me rewind just a little bit. I have, so I've got the point -1. I need to worry about to the left of -1, so I'm going to pick an easy point, -2. That's I think the easiest one to calculate there. 0, 2. This is actually the one I don't need, but I'm going to go ahead and fill in the gap between those and find -1/2. Then the next important thing I need to worry about is 1, so I'm going to find a point between 0 and 1, and that's going to be 1/2. And then the last one, it's a 0, is 2. I need to find a point between those, and I need to find a point to the right of that. So I'm just going to go ahead and calculate each of those by plugging them into f of x. The first one I get -4/3, then 5/6, then 4.5, then -2.5, and lastly, when you plug in 3, you get 2. So I'm going to plot each of those points. Some of them I have to approximate more than others. And those 3 points on the left of the vertical asymptote, and that's the point on the right of the vertical asymptote. And there's 3, 2, the last point. So now that I've plotted all those points, can you guys kind of see the shape of the graph? Let me just connect the line very slowly. There's one of them, and here is the other. And there we have it. We have graphed our function with a slant asymptote of y equals x. Thank you for watching.